It has been stated that aircraft are fitted with flap-type controls, and that flap-type controls generate the required moment about the CG by changing the camber of the aerofoil. There are two other types of control surface that do not change the camber of the aerofoil. The all-moving slab tailplane is sometimes used instead of an elevator for pitch control, when an elevator would not be powerful enough. The pilot changes the angle of incidence of the whole tailplane to generate the required pitching moment. The tailplane pivots around a hinge when the pilot moves the control column fore and aft. Backward movement of the control column decreases the incidence of the tailplane to generate an aircraft nose-up pitching moment. Forward movement of the control column increases the incidence of the tailplane to generate an aircraft nose-down pitching moment. Spoiler surfaces can be used to help the ailerons generate the required rolling moment. Spoilers literally spoil or disrupt the airflow over the wing, which decreases lift and increases drag. Spoiler surfaces will be explained in detail later. The force the pilot must apply to move the control surfaces into the airflow or hold the required angle of deflection must not be too high. When the pilot moves a control surface into the airflow resists. An aerodynamic force will try to rotate the surface around the hinge in the direction in which the force is acting. The product of the aerodynamic force and the distance from the hinge line to the centre of pressure of the control is called the hinge moment. It is the hinge moment the pilot must oppose to make and hold the required control deflection. The pilot refers to the hinge moment as stick force or feel. If the control deflection is increased, so is the hinge moment. As the IAS is increased, the hinge moment is increased for the same control deflection. Larger aircraft require control surfaces of larger area, and this will also increase the hinge moment. So the greater the displacement, IAS or surface area, the greater the hinge moment. For large and fast aircraft, therefore, the hinge moment could become so high that the pilot would have great difficulty in making and holding the required control input. Therefore, the pilot may require assistance to move the controls. This is done either by using some form of aerodynamic balance or power flying controls. The first type of aerodynamic balance we will consider is the inset hinge. We have seen that the hinge moment is a product of the aerodynamic force, F, and the distance of the centre of pressure from the hinge line, D. During manufacture, the control surface hinge is positioned aft of the control surface leading edge. This reduces distance, D, and thus reduces the hinge moment. Most aircraft with manual controls have inset hinges on the ailerons, elevator, and rudder. The designer must make sure that the control surface centre of pressure can never move forward of the hinge line. This would cause the control surface to self-select or increase in deflection. This is known as overbalance and can never be allowed to happen. A typical inset hinge looks like this. The area of the control surface forward of the hinge line is shielded to prevent it protruding into the airflow. The second type of aerodynamic balance we will consider is the horn balance. A small area of the control surface is positioned forward of the hinge line at the outboard end. The horn generates a small aerodynamic force that opposes and therefore decreases the hinge moment. The area of the horn balance is carefully calculated so that overbalance is prevented. The horn balance is used on the rudder and elevator, but not the ailerons. The third type of aerodynamic balance we will consider is the internal balance, which uses the pressure difference between the upper and lower surfaces of the aerofoil to reduce the hinge moment. The internal balance consists of a seal between the leading edge of the control surface and the trailing edge of the aerofoil. The seal is in the form of metal panels with appropriate hinges to allow movement. The internal balance is very effective and is still used on some modern jet transport aircraft and business jets, even those with powered flying controls, as they relieve the stresses on the structure where the hydraulic actuators are attached. The preceding three types of aerodynamic balance reduce the hinge moment by adjusting the aerodynamic force, or the arm, forward of the hinge line. We will now consider devices that reduce the hinge moment by generating forces aft of the hinge line. These devices are collectively known as tabs, a small aerofoil mounted on the trailing edge of the main control surface. The following illustrations are schematic. They just show the operating principle of the device. In reality, the mechanisms will be inside the structure. The first tab we will consider is the balance tab. The pilot input is connected to the control surface so that when the pilot moves the cockpit control, he or she is directly moving the control surface. There is a link between the fixed structure and the balance tab, such that when the pilot moves the control surface, the balance tab moves in the opposite direction. Please note, it is movement of the control surface that moves the balance tab. Therefore, if for some reason the main control surface can't be moved, the balance tab can't move. It is the aerodynamic force on the balance tab acting in the opposite direction to the one on the control surface which reduces the hinge moment. Because the balance tab moves in the opposite direction to the control surface, the effectiveness of the control is reduced. This is because the opposite motion of the balance tab reduces the change in camber commanded by the pilot. In practice, the designer will compensate for this. To summarize, the balance tab reduces the hinge moment, stick force and feel. The pilot moves the control surface moves the balance tab. The balance tab moves in the opposite direction to the control surface, giving a reduction in control effectiveness. The second type of tab we will consider is the anti-balance tab. The pilot input is connected to the control surface so that when the pilot moves the cockpit control, he or she is directly moving the control surface. There is a link between the fixed structure and the anti-balance tab, but this time when the pilot moves the control surface, the anti-balance tab moves in the same direction. Please note, the anti-balance tab is the only tab that moves in the same direction as the control surface. It is the aerodynamic force on the anti-balance tab acting in the same direction as the one on the control surface that increases the hinge moment, stick force and feel. Because the anti-balance tab moves in the same direction to the control surface, the effectiveness of the control is increased. This is because the motion of the tab now increases the change in camber commanded by the pilot. The anti-balance tab is fitted to aircraft that otherwise would suffer from either a lack of control effectiveness or stick forces that are too low. To summarize, the anti-balance tab increases the hinge moment, stick force and feel. The pilot still moves the control surface directly, and it is the control surface that once again moves the anti-balance tab. The anti-balance tab moves in the same direction as the control surface, giving an increase in control effectiveness. The third type of tab we will consider is the servo tab. The servo tab is very different from the preceding two tabs. The horn is merely pivoted on the control surface and is free to rotate. The pilot input directly moves the horn. But this time the link is connected from the horn to the servo tab. Thus, when the pilot makes a control input, it is the servo tab that is being moved, without any mechanical input to the control surface. It is only when the aircraft has sufficient IAS that the aerodynamic force generated by the servo tab can move the control surface. The aerodynamic force on the servo tab moves the control surface in the opposite direction. Because the pilot is only moving the servo tab into the airflow, the hinge moment, stick force and feel are reduced. If the aircraft has powered flying controls and a hydraulic failure occurs, a servo tab can be used for what is called manual reversion. That is, the pilot will still be able to move the servo tab and hence the control surface even at high IAS and maintain control of the aeroplane. Because the servo tab moves in the opposite direction to the control surface, the effectiveness of the control is reduced. The servo tab has other disadvantages. The first disadvantage is that when flying at lower IAS, the smaller aerodynamic force from the servo tab will give reduced control surface movement, when in fact the pilot requires an increased control surface movement. In practice, the designer will compensate for this. The second and more significant disadvantage of the servo tab concerns the fitment of control locks. If your aircraft is fitted with servo tabs, you must physically check that the control locks have been removed before flight. Because the pilot only moves the servo tab, the full and free control movement check in the cockpit will not alert you to the fact that the control locks are still engaged and you will not be able to control the aircraft. The control locks of some aircraft can be engaged and disengaged from the cockpit, and when engaged will prevent access to a vital item, such as engine start, in order to minimize accidentally trying to take off with the control locks engaged. To summarize, the pilot can move the servo tab only. The servo tab moves in the opposite direction to the control surface and therefore reduces control effectiveness. The servo tab reduces the hinge moment, the stick force and control feel. The servo tab has reduced effectiveness at low IAS, and you must physically check that control locks have been removed before flight. Because the pilot is only moving the servo tab and not the control surface, the servo tab can be used for manual reversion in the event of hydraulic failure to powered flying controls. This will be discussed in detail in the next segment. To overcome the reduced effectiveness of the servo tab at low IAS, a spring tab can be fitted, the fourth type of tab. The horn is merely pivoted on the control surface and is free to rotate. The pilot input directly moves the horn. The link is connected from the horn to the spring tab. When the pilot makes a control input, the spring tab is being moved directly by the pilot without any direct input to the control surface. So far, exactly the same as the servo tab. But now you can see there is a spring fitted between the horn and the control surface, so that when the pilot makes an input at low IAS, the control surface and the spring tab move together, giving maximum effectiveness. Progressively, as the IAS increases, there is a greater aerodynamic force on the control surface that resists the attempt of the pilot to deflect it into the airflow, causing the spring to be compressed. Compression of the spring makes the spring tab move in the opposite direction to the control surface, so the hinge moment, stick force and feel is reduced. The higher the IAS, the greater the spring tab deflection and the more assistance the spring tab provides. To summarize, at low IAS, the spring tab doesn't move relative to the control surface. The pilot moves the control surface and the spring tab together for maximum effectiveness. At higher IAS, the spring tab acts as a servo tab by moving in the opposite direction to the control surface, and therefore reducing control effectiveness. At high IAS, the servo tab reduces the hinge moment, the stick force and control feel. The spring tab can also be used for manual reversion in the event of hydraulic failure to powered flying controls. This will be discussed in detail in the next lesson.